We'll start again, and this is Recitation 2, and we are going to talk about computing the derivatives for vectors. And firstly, we will talk about the notations and conventions we will use in this recitation. And we will refer to the derivatives of a scalar L with respect to x as delta xl, and the derivative of a scalar L with respect to an column vector n cross 1 x is a 1 cross n row vector, and here the shape of the vector, the derivative will transpose. And when it comes to a n cross n matrix x, and if the shape of the derivative will be n m cross n, and when it comes to a vector y n cross 1, and the derivative of the variable would be a Jacobian matrix, and the shape would be n cross m. Next is the definition of the derivatives, and the math definition would be in the limitation form as in the formula. And does anyone know how to understand the derivative basically? Okay, so it would be a slight change in the variable and would result in the function value. And for the geometric understanding, the derivative of a function with respect to x at the point x0 would be the slope of the tangent line to the graph of f at x0. And it is shown in the graph in this corner. So when we are computing the derivatives, and one thing you need to notice is the shape of the derivative for any variable would be transposed. And it is just a convention, and there are two ways to do it, and we choose one of them. So when the variable is a column vector, its derivative would be a row vector. And for a matrix, and the shape would also be transposed, as in the plot. So next, we are going to talk about some computation rules. And firstly, start from the scalar, then move to the vectors. So here, z is a linear calculation of x. It is the wx. And all terms here are the scalars. And the partial derivative of L to z is none. So the partial derivative of L to x equals the partial derivative of L to z times w, which is a chain rule. And the partial derivative of L to w equals x times the partial derivative of L to z. Next is the addition. Here, z equals x plus y, and L is the function of f of z. The partial derivative of L to x equals the partial derivative of L to z, and times the z to x. And here, because the partial derivative of z to x equals 1, so here goes the right-hand side, which is the second equation. And the derivative for y is same computation as x. Next is a chain rule. Here, z equals the function g of x, and L equals the function f of z. And the partial derivative of L to x equals L to z times the derivative for x. Next one is the generalized form of the chain rule. Here, L is the function of f of gix, and we assume all the partial derivative of L to gi are known. So here, the partial derivative of L to x is the summation of the partial derivative of L to gi, and then times the partial derivative of gi to x. And on the right-hand side, this one is the dependency diagram, which is quite useful when you're computing the derivatives. And here, gi depends on x, and L depends on gi. So here comes this formula. And as we have talked about the scalar forms, next we will move to the vectors, which is usually used when we are doing machine learning. And first one is the multiplication. here, most of the things are similar as previously, but for z and x here are different. They are column vectors, and W is a n cross m matrix, and L is a function of a z. So the partial derivative of L to x equals the partial derivative of L to z times W. But here, when we are computing the derivative for vectors, one thing need to mention and to make sure is to make the dimensions match. So here, the partial derivative of L to z, its shape is, it's a row vector because z itself is a column vector. So it's 1 cross n. And W itself is n cross m. So when they times together, it is 1 times m, which is the same as the shape of the partial derivative of L to x, which is a row vector, 1 times m. And for the derivative for W, it's the same, and you can check it. And next is the addition. Here, most of the things are same, so we're also using the chain rule. And so the partial derivative of the z to x is 1. So here, the partial derivative of L to x equals the partial derivative of L to z, and y is the same. Next is the chain rule. Here, one thing different is the Jacobian matrix of Gx with respect to x. So we're going to notate it as a Jxg, and sometimes it may be a diagonal matrix. So here, the partial derivative of L to x equals the partial derivative of L to z, and times the Jacobian matrix Jxg. And the shape of the partial derivative of L to z is a row vector, which is 1 cross n, and the Jacobian matrix of Jxg is n cross n. So times together, it becomes the 1 cross n, which is the same as the shape of partial derivative of L to x. Then is the generalized form of the chain rule. Here, the Jacobian matrix of the Gix with respect to x is of the shape m cross n. So m is the output shape, and n is the input shape. And the other things are similar. And next one is the element-wise multiplication. Here, z equals x dot y, and L is the function of f. Here's a small mistake. Here should be fz. And dot represents the component-wise multiplication. So here the partial derivative of L to x equals the partial derivative of L to z, and element-wise dot y transpose. So you still need to make sure that the dimensions are matching. Next one is the element-wise function. Here, z equals gx, and g itself is a vector of the component-wise functions. And usually, it will come with the ReLU or the sigmoid functions when you're using the activation functions. So here, when you are computing it, the partial derivative of, L to x equals partial derivative of L to z, and element-1 dot the derivative to x transpose. So it's quite useful when you're doing the derivative with respect to the activation functions. So as we have talked about most of the computation rules for the vectors, and they are simple ones, so we are now prepared to compute more complex derivatives. So usually we are given a forward computation, and the key to compute a derivative is actually just to work backward. And the whole procedure would be firstly to express the computation as a series of computations of the intermediate values, and then to split those computations into either unary or binary forms. So for binary relation, it usually comes with the addition or multiplication as this one. So we are going to use two examples with the MLP to illustrate how to compute the derivatives in the backward. And here we suppose there is a MLP network and it has two hidden layers. And this one is the dependency diagram, and it's the similar with the on the previous slide. And it is quite useful when you are computing the derivatives. And the whole operation for the feedforward network, there are 5 operations. First one is the linear layer, and then goes with the ReLU function, and then connected with another linear layer, and then is the ReLU function, and the output is another linear layer. But one thing you need to notice is that these operations are still not in the either unary or binary forms. So next step, we're going to split those operations into only unary and or binary operations. So as you can see, for the step 1, 2, 4, 5, 7, and 8, they are binary operations, and they are either multiplication or addition. And for step 3 and 6, they are the unary operation, and they are also the element-wise function. So as we have split those operations into unary or binary operations, we are prepared to compute the derivatives in reverse way. And firstly, we need to mention two things. We assume the derivative of the partial derivative of L to output is given, and what we actually need to output is the partial derivative of L to x and the partial derivative L to wi and bi, and here x is the input and wi and bi is the parameters within the linear layers. So as we are going to work in the reverse way, so first step would be the last step. So output is actually addition of Z7 and B3. So record the previous slide on the vector addition. The partial derivative of L to Z7 and B3 equals the partial derivative of L to output. And next step is a multiplication operation. And here, one thing still need to notice is to make sure the dimensions of the derivatives match. So the partial derivative of L to W3 equals Z6 times the partial derivative of L to Z7. Next step is the ReLU function. And for ReLU function itself, here it is element-wise function. So for the ReLU, its derivative would be an indicator function. And to recall the previous slide, so the partial derivative of L to Z5 equals the partial derivative of L to Z6. Element-wise dot the derivative of ReLU function to Z5. And next step is another addition operation. And then is the multiplication operation. And then is another ReLU function. And then is a addition operation. And finally, for the partial derivative of L to x is what we actually need to output. And we need to also save the partial derivative of other other hidden layers parameters, which is wi and bi. And for these zi intermediate values, we are just using it and to pass the intermediate values. So then Amala is going to introduce about how with the example of the scanning with an MLP.
not streaming, so people can't access so basically the link might have changed. So in the previous example, we saw a neural network with two hidden layers that took a fixed dimensional vector of size n cross 1 as input and produced another fixed dimensional vector as output. And we saw how to compute the derivatives of the scalar quantity L with respect to the inputs to the vector and also the network parameters. Now, in this example, we're going to change the situation a little bit, and we're going to see how we can compute the derivatives when instead we're scanning the input with our neural network. So in this setting, the input will be of size t cross 1, where t is potentially greater than or equal to n, and the MLP architecture will be more or less the same as before. In this case, the neural network will look at n consecutive elements of the t-sized input vector at a time, and it will produce a corresponding output OT at that time step. So as you can see in the second point here, xt is the input at time step t, and we're looking at a window of size n. I think this process will probably become a bit more clearer when we see this illustration. So in this example, the neural network is taking 3 input elements at a time. So in the first time step, it looks at the first 3 elements and produces the corresponding output O1. In the second step, it looks at the next 3 elements and produces the output O2. In the third step, it looks at inputs 3 to 5, and it produces output O3, and so on till we reach the end of the array. So, so what we're essentially doing is that we're scanning a window of size n across the input, and we're passing the contents of this window to our MLP to produce the corresponding output at that time step. So this is a combined picture of what we're doing at all the time steps. And something important to notice here is that, like, since the network at time step t is not looking at any of the intermediate outputs or the final outputs at any of the other time steps, we could be performing this process parallelly as well across all the time steps. So, let's formally define all the forward equations for this process. So we're defining L, which is a scalar quantity, as a function of all the outputs from time step 1 to t minus n plus 1. I mean, we're going to have t minus n plus 1 steps because our window is of size n and the input vector is of size t. So the forward equations look more or less the same as they did before. So in the for the first layer, we pass it through a linear layer, then through a ReLU, then another linear layer and a ReLU, and another linear layer. But an important difference to notice in these equations is that over here at time step t, while we have indexed the intermediate outputs, which are the ZIs, and also the input and the output with t, we have not indexed the network's parameters with t. So what this means is that we are using the same set of parameters at every single time step. So we are sharing the parameters. So are there any questions about what we're doing in this process? Is there any confusion? Yeah? Yeah, the second element is the first element in the second scan. We could be doing that. Like, this is a specific case where the stride of the window is 1, but you could like choose any other stride, and then suppose if you had a stride of 3, then you could hop by 3 steps and look at the next 3 vectors instead. So what? I mean, okay, so Professor Bhiksha is going to talk about scanning with MLPs in much more detail in future lectures when he's teaching about when he starts teaching you CNNs. So he's going to motivate the problem and you know, why we do it, why we would want to do it, and what strides might be better for this. But like in this recitation, we're just going to focus on how we can calculate the derivatives for such a process. Yeah. So now we would want to compute the backward, do the backward computation for this MLP, right? So an important, like at this step, I'd like you to recall the generalized chain rule that we had seen before. So and especially this influence diagram on the right hand side. So if the variable x is influencing the variable L through multiple paths, then if we want to calculate the derivative of L with respect to x, then we will have to add up the individual contributions along all the paths. Now, in our problem statement, the same values of W1 and B1 are being used by the neural network at every time step. So when we are calculating the derivatives of our quantity L, which might be the loss, or like F might be any crazy neural network as well. So when we want to calculate the derivatives with respect to L, we'll have to add up their individual contributions across all the time steps. Yeah. So as the first step, we'll first just similar to what Yang showed us earlier, we'll have to simplify all our expressions into unary and binary operations. And so on the right hand side, we see the original equations, and on the left hand side, we'll see all the unary and binary equations that are going to be used in the process. Now, when we're calculating the derivatives, again, we'll follow the same procedure. We'll start from expression number 8. We'll calculate the derivatives of Z7 and B3, assuming that we know the derivatives of OT, and we'll continue in this process till we move back to the first step. So reiterating what I said earlier, we're assuming that the derivative of the scalar quantity L with respect to the outputs at every time step are known. So that's just dou L by dou OT, and we want to compute dou L by dou X, where X is our t cross 1 input vector, and also dou L by dou Wi and Bi, and both of these are the network parameters. So at time step 1, like I won't be repeating the steps that he did earlier, so we'll get more or less the same equations. They all look the same, except that we've indexed the Zi's and the input and the OT with the index t, because it's happening at time step t equals 1. The only difference is in step number 15. So in step number 14, we calculate the derivatives with respect to the window of size n at time step t. And in the 15th step, we're setting the derivatives of capital X for that particular window to be equal to the derivatives for small xt, which is the input to the network. I hope this operation is okay. Like, any questions about this? Okay. Now, what at subsequent time steps where t is greater than 1, again the equations look more or less the same, but there's a crucial difference. So if you look at equation numbers 2, 3, 7, 8, 11, and 13, we're using a plus equal to instead of an equal to. So this comes from the generalized chain rule. Since W is contributing, influencing L through multiple paths, like at every time step, we add up these derivatives, we keep accumulating them. And another difference is at time step 15 and 16. So earlier we set the derivatives for the entire first window equal to the derivatives for x small t. But in this case, as another student pointed out earlier, we're just moving the window with one time step, right? So the second input in the first time step becomes the first input in the second time step. So the derivatives of the first n minus 1 elements already exist in from the previous time steps in the derivative vector for capital X. So we just add to these derivatives from the corresponding, like the first n minus 1 elements from small xt, the derivatives, and for the last element in the derivative for that window, we just set it equal to. Now, I know this might be a bit confusing, so are there any questions about this right now? Okay, so moving forward, there's a question of when to use equal to and plus equal to, right? And we have to keep track of which variables are being used for the first time versus which are being used again. So there's just a simple trick to deal with this. We can initialize all of the derivatives to 0 in the beginning, and we can just keep using plus equal to in all of the steps. So we'll be using this these set of steps at every time step at t greater than or equal to 1 instead of just greater than 1. Yeah.
Then you won't need to do that extra step at the end where you just initialize.
Which one?
Like, could you go back?
Yeah.
Like you won't need to do the 16th step, right? If you initialize at 0.
Yeah, that's correct. We can just use the 15th step over here with the plus equal to accumulate the derivatives. Yeah, I think that's all we had planned for today. So if you guys have any questions or any doubts related to homework 1, you can ask us now. Yeah.
So if the window is scanning, if that window doesn't overlap, you don't have to plus equal, right? Plus equal is always when you overlap.
Yeah, so if we had a greater stride, like if we were moving the window with hopping the window, yeah, we wouldn't need the plus equal to for the input. Yeah.
So, like, this is a pen paper calculation, so we know that we are doing it as a plus equal to
Yeah.
plus. But does the PyTorch library take care of that?
Yes, it does. So that's why we have that zero grad operation for setting all the derivatives to 0. That's because PyTorch automatically does the plus equal to operation for us. But if we were writing this backward functionality from scratch, we would have to implement the plus equal to. Like that's something that has to be done manually.
So zero sets all of the variables to 0, right, after each step. So if we want to include this functionality, we'd have to remove that.
Sorry, I don't understand.
So like in general, when you don't have a sliding window, we use a zero grad to set all the variants which are there in the network to 0 before we start a new one.
Yeah.
So for a case like this,
Yeah.
we need to remove that zero grad from, like we don't need to use it anymore, right?
Oh, yeah. So far, as you've seen in the code, we use the zero grad function after we process a batch. So we can do that here as well. Like in a batch, we'll slide suppose the batch consists of only one input vector. So we'll do all the sliding operations, and after they're all done, and you do you use the optimizer and do everything else, then we'll set zero grad to. Then we'll use the zero grad operation.